So this is question number 14. Laminar flow in the entrance of a pipe as shown below. The entrance flow is uniform, U equal to U naught, and the flow downstream is parabolic in profile. So this is the velocity profile for the flow in pipe. Using the integral relation, section 213 shows the viscous drag exerted on the pipe wall between 0 and x is given is this one. Okay, so we need to show means we need to do some derivation here. So I think everybody is understand this diagram. So means at the entrance here, we assume that the velocity is uniform because maybe the friction on the side is not works yet. Okay, so and then when the fluid flow at certain distance, so the resistance on the pipe wall here is fully effective. So means that the condition called no slip condition has occurred. So because we have no slip condition, so means that the velocity here is 0, and then the velocity profile is happen like this. So the curve here, or the equation to show this curve, is actually given in these terms. UR C R naught square minus R square. So and then for this one, to show this one, okay, I just to revise the idea of Reynolds transport theorem. So this is an mathematical expression. So we have capital C here, which is the constant C. That means that we need to calculate what is the value of this constant. Okay, so this is the idea of the remote transport theorem. So the idea is mass flow rate in is equal to mass flow rate out. Okay, so this is maybe suitable for the incompressible flow. So the idea is the inlet is rho AV. So you know rho AV is the mass flow rate. Is the integration mean the sum of the mass flow rate at outlet. So the idea is very simple. Normally, if we have a system here, for example, we have a 2 inlet and we have 3 outlet like this. Okay. So and then we need to sum all the inlet here and all the outlet here. So normally in the outlet we will show in integral symbol like this one. So how we could start this calculation? So we could see the equation here. So the equation for mass flow rate is rho A and V. So okay. So and then we have a flow in pipe like this one. So we have a pipe here. So and then we have a velocity profile like this one. So and then what we need to do is we just imagine we take a very small part here. So let's say this is the part that we need to take care. Okay. So and then that's why we write the equation here, because we have the integral process here. So we write as rho U and dA. Why we use dA here? Because the area here is very small. So we have a small portion of area here. So and then why the U here is not the du? Because the velocity inside this one is actually constant, because it's in a small area. The velocity at this one is actually can be represented by this equation previously. So we substitute, we have the rho naught here, it is constant, so we could bring it outside the integral process here. So we have the velocity, and then we could get the value of dA. So dA here is 2 pi r dr. So it is come from, okay, we know that the area, because pipe is always circular. Okay, so we have the A is pi r square. So and then if we have a dA over dr, So we have 2 pi r. So we have 2 pi r, and then if we have dA, we could get 2 pi r dr. So this why these terms come from. So and then if we do this, so we could integrate with dr. So and then we substitute the limit of 0 to capital R. So the capital R is, we assume that this is the center point, for example. So let's say this here is the center point. So we assume that the maximum value of radius is written as capital R. So that's why we write the limit of the integration is 0 to R. So we get this term. So this is for the AU. So here the row can be cancelled. So we get this term. So and then, okay, so we get this term. So we could have this one, and then we could rearrange the calculation. We get the value of C is equal to U naught over R squared. So and then we substitute into the previous equation here. So we get the full equation here as UR, mean velocity of U in terms of R direction, or function of R is 2U naught over R square, R naught square minus R square. Okay, and then we discuss about the viscous drag or drag force. Okay, so we know that the drag force is F equal to ma. So and then we could simplify into this term. So because normally in fluid mechanics we try to use terms of velocity instead of acceleration. So ma here, so a is acceleration, so we change the a here with the d dt for velocity. Okay, that's why we have this one. And then these forces, okay, these forces is actually comes from the control volume and also come from the surface. So here, this is the common terms for the Reynolds transport theorem. So we need to write as this one. So we write the d dt, integral control volume for v rho dv, which is the dv here is the volume, and integral of control surface, which is the v rho vn dA. Okay, so and then here, okay, I will add here. So this must be vn. Okay, so and then we need to draw the control volume, the control volume of our system. Okay, so what is the meaning of control surface? So control volume here. The control volume here means the force here maybe comes from something in the volume. Okay, and then plus something that's occur on the surface, something like that. So means the changes inside the system and the changes because what happened on the surface here will contribute to the force, So that is the meaning of this one. So and then if we look at the units here, so this is the velocity, mean meter per second. So we have the rho, the density, kilogram per meter cube. So and then we have the volume, which is the meter cube. Okay, so and then we have the T here, so we have 1 over time. Okay, so that is the way we analyze the units there. So if you find that the units here is actually equal to the Newton units. Okay. Okay, so and then how we determine this one? Okay, and then we see the word of the derivative here. So we have d volume and we have the dA here. So the d volume here, normally because we are the situation is steady flow, or they are no different in terms of volume normally, because maybe we have a very rigid pipe there. So means that the volume here is not changing. So if there are no changes of the volume, so means that this value is actually will become 0. Okay. Normally in fluid mechanics word, so the if the steady flow, so the term of this one can be neglected. Now we are only focused of the control surface. So control surface usually caused by, because in fluid mechanics, if fluid flow at certain velocity, so for sure the pressure occur. So and then because we have surface here, we have the cross-sectional surface here, means that when pressure acts on surface, so they will give pressure, they will give force. So we could have the force here, and we could have the force push on the surface. However, the volume or the velocity is moving inside the system and outside the system like this one. So and then we draw an n vector here to fulfill the equation, because the equation here is actually v rho v n dA. Okay, this velocity actually need to follow the direction of this axis. Okay, so the direction of n axis must be from surface to the outside. So if the surface is here, so means the n axis must be from the surface outside like this one. So this is the surface, so it must be from the surface outside like this one. Okay. Okay, just to simplify this one, so I neglect the value of R naught here. Okay, so the R naught here means what happened at the beginning. So the U naught here is just U, and R naught means the capital R. So now the equation is become like this. So the meaning of the force here, as I said, if we have one system like this one, so we have a 2 input, for example, and then we have 3 output, we need to add all of them. So means this equation means total force that occur must be equal to the force that occur on the surface. Okay, so this is the meaning of this equation. So and then, okay, the total force is for sure. Okay, for sure, if we have this system, if the velocity is moving from left to right, the resistance or the drag force must be X in the reverse direction. So means that we assume that the FD is X from right to the left, because the flow is moved from left to the right. Okay, so and then the drag force is the first force in the system. So we write negative FD. So and then because we have pressure that push to this surface, okay, to this control volume, so we take this one as the second and the third pressure. So because this is positive and this is negative direction, so we write plus P naught A naught and minus PX AX. So and then we need to calculate the changes because of the surface here, control surface. Okay, so we just follow the equation here. So we have V, velocity, density, and velocity n dA. So the velocity, so normally we go for the first surface here. So at this surface, we found that the velocity is this one. Okay, so this is the positive side. No, okay. So and then we write as a positive U. We have the density rho, and then the V here is actually the velocity for the n axis. So because the n axis, the positive is from right to the left, but the velocity is moving from left to the right, so we write as negative U. So and then the A here is the cross-sectional area at this one. So this is maintained as A naught. And then we have uh, the integration of this one. Okay, so and then this is the that one, and then for this one here, okay, we cannot just use straightforward the value of u r, because the idea is at the input here the velocity is almost constant because there are no resistance. However, at certain point in the pipe, the velocity is changing. So means we need to do the derivation because the velocity is changing. So means that we need to do the integration to get the overall value of these changes. So means that we have the integration 0 to r. So we have the u is the first velocity here is ur, and then we have the density. We have a density here, and then we have the according to this one, the ur, so the okay, the ur here is same direction with the n. So means the third terms here is in positive value. So we have the another ur here, and then we put an a dA here. Why we put a dA here? Because okay, because we have a velocity profile there, and then the ur here is only for one small area. So this is the dA. Okay, so and then we substitute this one. Okay, means we try to simplify everything. So we have this term. Okay, so and then we need to solve this one. So if, for example, we bring this okay, so in this terms, maybe in this node, I solve this one first. So this is the value of r ur square rho 2 pi r dr. So and then we could solve it. So the ur square here is actually this term. So and then I could simplify this one. Okay, so this is maybe there are no del here. So we have this term, and then because the integration is to the dr here, so we bring out all the constant terms outside. So then we have this term. So and then if we substitute with the limit 0 to r, so then we could get this term. So it means that we know that this term can be simplified into this one. So and then we replace the integration part here with the amount that we have, and then we could solve this one, we get this one, and finally if we rearrange the terms, we could get the FD here is equal to pi r square P naught minus Px minus 1 over 3 rho u square, means that we could fulfill the question to show that the drag force is actually equal to this term.